All right, this is the first of two shadow-related rate problems. Shadow-related rate problems. Yeah, there we go. Anyway, I want to do them with you. I'll do one in this video and one in the next. We got a person walking at 3 miles per hour, and this person passes directly underneath a street light. As this person walks away from the light, the length of their shadow changes. If the street light is 20 feet high and the person is 5 feet tall, find the rate at which the length of the person's shadow is changing. Okay, um, so you got the street light here. You got the person that just walked underneath it. I'm going to draw the person over here. Okay, so the light comes out of the street light and it hits the person, and well, doesn't make it to the ground if it hits the person, but stuff out here, the light would actually hit the ground. So the shadow of the person is from their feet up to where, straight line between the light and the head and the ground. That line right there would be. So this is the shadow. Okay. Now, a person is walking at 3 miles per hour. 3 miles per hour is a rate of change, right? It is a rate of position change. So if we were to call, let's drop a perpendicular right down here from the light, say this length right here is x, that is the person's position is given by x, measured from anywhere, but we're going to do it from straight underneath the light. So dx dt is 3 miles per hour. Okay, we're looking for the rate at which the length of the shadow is changing. So let's call this length here something else, maybe like y. dy dt is what we're looking for. I don't know what it is. I'm trying to find it. Dy dt is what? Right. Now, in this problem, I didn't actually give a position where the person is, and so we'll have to fill that in later. It may be that the length of the shadow is changing at a constant rate. Maybe it's changing at different rates for different times. We'll have to see. But what I need now is a relationship between x and y that's always true. And in order to do that, I'm going to look at similar triangles. I can either think of this in terms of trig or in terms of geometry. I know that the height of the person is 5 feet. I know the height of the streetlight is 20 feet. So there's two triangles here that are similar. There's a big triangle there, and then there's this little triangle. And the ratios of corresponding sides are equal. And you can think of that, say, in terms of this angle right here. If I look at the tangent of this angle, I can say, or let's do the cotangent. The cotangent of the angle is y over 5. But from the point of view of the big triangle, the cotangent of the angle is x plus y over 20. Right? Again, I thought of that in terms of trig, but some people just say, oh, I've got similar triangles, ratios of corresponding sides are equal, so horizontal side to vertical side is the same as horizontal side to vertical side. Okay. But anyway, what I have here now is a relationship between x and y. I'm going to multiply both sides by 20 just to get rid of the fraction. So I've got 20y. No, I don't. I'm going to multiply both sides by 20. The 5 and the 20 will cancel out to leave a 4. So I've got 4y equals x plus y. Okay. And wow, that's actually kind of nice. I can get the y's together, and I get that 3y is equal to x. There's a relationship now between x and y. I'm going to implicitly differentiate to get a relationship between dx dt and dy dt. So 3 times dy dt equals dx dt. Well, that was a nice relationship. That sure was. So what do I know? I know dx dt is 3, and dy dt is what I can find. So 3 dy dt equals 3, so dy dt equals 1. Apparently, with this person walking 3 miles per hour, the rate of change in the shadow is 1 mile per hour. And it seems that it doesn't make any difference where the person is, that it's always the length of the shadow is increasing at 1 mile per hour. I mean, it seems kind of funny to be talking about lengths of shadows in terms of miles per hour, but because we knew the speed of the person walking was 3 miles per hour, then we're doing this in 1 mile per hour. Notice there's two different questions that could have been asked. We asked one of them, but the other one is, how fast is the tip of the shadow moving? You know, the shadow of his head moving. Well, the thing is, his feet are moving at 3 miles per hour, and the shadow is apparently growing at 1 mile per hour. So the tip of the shadow is actually growing at 4 miles per hour. What did we do? We were given one rate. We had to find another rate. We found a relationship between the two variables. That's always true, no matter what time it is, right? As everything is changing, as the person's moving, as the length of the shadow is changing, there's this relationship that's always true. The similar triangles. Got that relationship. We actually simplified it first, and then we said, okay, now I can implicitly differentiate with respect to time to get a relationship between the rates. Plug in everything you know, solve for the one you don't, and you're done. So there you go.